Hi, I'm Chris Seaton. I'm a senior staff engineer at Shopify, which is a Canadian e-commerce company. I work on optimizing the Ruby programming language, but I do that by working on a Ruby implementation on top of Java and the JVM and Graal called JavaRuby, which is why I'm here today. I'm the founder of JavaRuby. I write about compilers and optimizations and data structures. I maintain the rubybib.org, which is a list of academic writing on Ruby. In this talk, when I talk about compilers, I mean the just-in-time or JIT compiler. That's the compiler that runs as your program is running. So I don't mean Java C in this context. I spend a lot of time trying to understand what the Java compiler is doing with my code and how I can change my code to get the result I want out of the compiler. And I also spend a lot of time trying to teach other people to do this. There's a few tools for understanding the compiler. You can look at the assembly code that's produced by the compiler. You can use a tool like JIT to look at the logs that the compiler produces as it produces the code. The ultimate option is to reach into the compiler and actually look at the data structures it uses to understand, optimize, transform, and compile your code. But all these options are quite complicated and they aren't very accessible. I'm experimenting with some new ways to understand what the compiler is doing, including by trying to give you back pseudo Java code from the compiler after it's finished running or part of the way through its running. So the idea is that anyone who can understand Java, which should be most Java programmers, can look at what the compiler is doing in terms of Java code, which they already understand. At Shopify, I maintain a tool called Seaton to help us look at these data structures and to do this decompilation from optimized Java back to pseudo Java. It works within the context specifically of Graal, so if you're not a Graal user already, it may not be immediately applicable to you, but maybe it's another good reason to experiment with adopting Graal. Using it, we can gain a bit more of an understanding of what the JIT compiler really does. I'm always amazed that people argue online about what the JIT compiler does do or doesn't do for some given code. Let's simply dive in and check. Most of the time your Java program will start as source code in Java files on disk, and you'd normally run those through the Java compiler, so Java C, to produce bytecode, which is a machine readable representation of your program. Not everyone's aware that there's a second compiler, the just-in-time compiler. This takes your bytecode while the program is running and converts it to machine code, which can run natively on your processor. There's also another sort of compiler you can use, an ahead of time compiler that produces the same machine code, but instead of you keeping it in memory like the JIT does, it can write it out to a file on disk, so an executable file or a library or something like that. That's a bit more popular these days due to native image, which is part of the Graal VM. It's been an option for a long time, but it's getting more popularity these days. In this talk, the compiler we're interested in and the configuration we're interested in is using the JIT compiler to compile bytecode to machine code at runtime. But some of the ideas apply the same for the AOT as well, but we'll just keep it simple for this talk. So we had a little arrow there for the JIT, but really the JIT is a big thing. It's a very important thing for the performance of your Java application, getting the kind of performance out of your application you'd like. And it does a lot of things, and one of the problems with it is it's a bit of a black box. So if you're not sure why it's giving the machine code it is, why it's optimizing in the way it is, what it's going to do with a given program, it's quite hard to figure that out because it's generally seen as a sort of monolith that's quite hard to see inside. But really there's lots of things going on there. There's multiple processes. It parses the bytecode, so it repasses it like it passed your Java source code originally. It produces machine code, and in the middle it uses a data structure called a graph, which is what this talk is about. And it's about looking inside the JIT compiler at that data structure. Why would we want to do this? Well, just for interest, for one thing. It's interesting to see how these programs work, especially if you spend a lot of time using the Java JIT. It'd be interesting to see how it's running and why, just for interest. You may want to understand what the JIT is doing for your program, for your work. You may want to understand what it's doing with it. You may want to figure out why it isn't optimizing as you were expecting. If you're trying to get a particular sort of performance out of your program, you may want to understand why the JIT compiler is doing what it is in order to get the best out of it. Perhaps you're working on a language that runs on top of the JVM. So for example, I work on Truffle Ruby, which is a Ruby implementation, but it runs on the JVM, which is why I'm speaking in a JVM track at a conference. Or if you're working on the Java compiler yourself, obviously that's a bit more niche, but there are people doing that. But what we can use it for is we can use it to resolve online discussions where people are guessing at what the JVM and the JIT does, and we can find out for real by actually looking inside and asking the JIT what it does. Nobody's advocating that this should really be a normal part of your daily work to analyze what the Java JIT is doing as part of your workflow. Nobody's suggesting that, but it can be useful sometimes. So this talk is all in the context of the GraalVM. So the GraalVM is an implementation of the JVM, plus a lot more. It runs Java. It also runs other languages such as JavaScript, such as Python, such as Ruby, such as R, such as WASM, and some more. It also gives you some new ways to run Java code, such as the native image tool I mentioned earlier, which allows you to compile your Java code to machine code ahead of time. This is available from graalvm.org. If you're not using GraalVM, then a lot of this won't be applicable, I'm afraid, but maybe it's another good reason to go and look at GraalVM if you haven't done it already. So, understanding what the JIT compiler does. Well, we said that the output of the JIT compiler was machine code. So the simplest thing we can do is look at the machine code. And human readable version of machine code is called assembly code. If you use these two options, so if we unlock the diagnostic VM options, and if we print assembly, then it'll print out the assembly for us every time it runs the JIT. Note this option depends on a library called HSDIS that isn't included with the JVM, and it can be a little bit annoying to build, which is an unfortunate thing. You can't just use these flags out of the box, unfortunately, and get actual assembly. So that's what it would look like. It gives you some comments which help you sort of orientate yourself, but it's pretty hard to understand what's been done to optimize here, and it's definitely hard to understand why. So this is the most basic of tools. A better tool is something like Chris Newland's JIT Watch. So if you unlock your dynastic VM options again, you can trace class loading, you can log compilation, and the JIT will write out a log of what it's done and to some extent why it's done it. And then you can use JIT Watch to open this log. It's a graphical program, or it can run headless. It'll do something to explain what's going on. So, so for example, in this view, it's showing us the source code, corresponding bytecode, and the assembly. And if we zoom in, you're still getting the same assembly output here, but now you can get a bit more information about which machine instructions correspond back to which bytecode and which lines of the program. So this is a better option. I'm not going to talk more about JIT Watch here. It's got loads of really useful tools, so I would consider using JIT Watch most of the time. What's the problems with assembly and these JIT logs though? You're only seeing the input and the output still, not really the bit in the middle. So JIT Watch will show you the bytecode, which is sort of, some people would think of as a bit in the middle, but really it's the input to the JIT compiler, and it only shows you the output as well, the assembly code. You're trying to understand what was done and why by looking at the lowest level representation. So when you look at assembly, most information is gone, so it's not useful to answer some detailed questions. And the assembly code is very verbose as well, so it's hard to work with. Graphs. So we said in the middle of the JIT compiler is this this data structure, and this is a compiler graph. So that's graph as in, you know, nodes and edges, not a graph as in a chart or something like that. And it's this data structure we're going to look at. So we're actually going to reach inside the JIT and we're going to look at this data structure in order to understand what the compiler is doing and why. How can we get the compiler to give us its internal data structure? Well, Graal's got this simple option. So graal.dump equals :1. :1 is a notation you can use to specify what things you want. It's got some complexity, but :1 gives you some what you probably want for most stuff. And here's an interesting thing. Why is this a D system property? Well, that's because Graal is more or less just another Java library, so you can communicate to it using system properties like you would any other Java library or application. And this then prints out the graphs when the compiler runs. What can we do with these graphs? Well, like JIT Watch, there's a tool called the Ideal Graph Visualizer, usually shortened to IGV, and this lets you load up the graphs into a viewer and analyze them. This is a tool from Oracle. It's part of the GraalVM project. It's being maintained by them at the moment. We can zoom in on the graph. I'll explain what this graph means when I start to talk about the tool I'm specifically using. But this is what Ideal Graph Visualizer will show you. At Shopify where I work, we use a tool which prints out the graph to an SVG file or a PDF or a PNG, and that's what I'm going to use instead. So it's the same data structure, just looks a bit different, and it's generated by an open source program instead. Yeah, so Seafoam is this work in progress tool for working with Graal graphs, and we can produce these kind of images from them. So what on earth do we do with these graphs? How do we read them and understand them? Well, here's a simple example. So I've got an example arithmetic operator, so a method. It takes an x, it takes a y, and it returns adding together the x and the y, and they're both integers. So to read this graph, we've got boxes, nodes, and we've got edges, which are lines between them, and it's a flow chart basically. So in this case, p0 is a parameter. First parameter, p1 is the second parameter. They are the x and y for this add operation, and the 4 just means it's node number 4. All the nodes are numbered. And the result of that flows into returning. So we return the result of adding parameter 0 and parameter 1. And then separately we have a start node. And what we do is we run from the start node to the return node, and then every time we need a result, we then run whatever feeds into the result. So it's a flow chart, and it's a data graph, and it's a control flow graph at the same time. It'll become a bit more clear when we look at a slightly larger example. I've got a website where I talk about how to look at these graphs and how to understand them a bit more. So a slightly more complicated example is an example compare operator. So this compares x and y and returns true if x is less than or equal to y. So we have our less than operator here. Again, we have the two parameters. If you notice, this is less than rather than less than or equal to. And what the compiler has done is it's using a less than rather than a less than equal to, and has swapped them around. So instead of saying this is less than equal to this, it's saying this is less than this. The reason it's done that is something called canonicalization. So the compiler tries to use one representation to represent as many different types of programs as possible. So it uses one comparison operator if it can. So it uses less than rather than using less than and less than equal to. Now that returns a condition, and then booleans in Java are 0 or 1 under the hood. So we then say if it's true, return 0. If it's false, return 1. And again, we have a start node and a return node. It starts to get more clear how these edges work when we start to talk about local variables. So here we do a is x plus y, and then we do a times 2 plus a. If you notice here, we have a plus, x plus y, and then that is used twice. So this represents the value of a, but it's never stored in something called a. In the graph, it simply becomes edges. So anyone who uses a simply gets connected to the expression which produces a. And also notice we have the multiplied by 2 has been converted by the compiler into a left shift by 1, which is a common compiler optimization you may be aware of if you've done a sort of undergraduate level compiler course. That red line becomes more complicated. The red line is the control flow. If we have some control flow, so we have an if, we have the red line diverges out. So now there's two paths to get down to the return depending on which side was taken of the if. The reason for the store field in here is just to make sure there's something that has to happen, so the if sticks around, doesn't get optimized away, and that you see the if takes a condition. And as I said, because the boolean is represented as 0, 1 in Java, it actually compares the parameter against 0, comparing it against false. Why can this be hard, right? This is a useful way to look at programs. Well, I've shown fairly small programs before, and there's lots of reasons why this gets really hard really quickly. So this is this is still a trivial Java method written out as a graph, and I can't even put it on one slide. It gets so complicated so quickly, and it gets almost impossible to read. They get very large very quickly. The graphs are non-linear as well. So this is an abstract from a graph. You can't read this, right? You can't read it from top to bottom very well. You can't read it from left to right. It's just a sort of amorphous blob. We call it a sea of nodes or a soup of nodes. If you notice, there's things beneath the return, but obviously they aren't run after the return, so it can be hard to read. They're inherently cyclic, so they're not trees, they're not ASTs, they're graphs with cycles. So here, this code has a loop in it, so it loops from this node here back up to this one and runs in a cycle. So this is a while loop or something like that. And I think humans just aren't particularly great at understanding cycles and things, so trying to reason about where in the program it is from the cycle is complicated. They can be just hard to draw, so even when they're not large, they can be tricky to draw. And this is an example of IGV, Ideal Graph Visualizer, the other tool, getting it slightly wrong. So this has lots of things sort of crossing over each other when ideally they wouldn't. And this is part of the reason why we built Seaton at Shopify. So laying out these graphs can be very tricky, and it gets trickier as they get more non-trivial. So what could we do instead? This is the idea I'm sort of floating at this conference and in some other venues. How about we decompile these graphs, right? The JIT compiler takes these graphs that's using to compile your Java code, and it produces machine code from them. Perhaps we could take the graphs and produce something else instead. Perhaps we could produce some sort of pseudo Java code, so something that's sort of readable like Java is. So not a graphical representation, but still allows us to understand what the compiler is doing by looking at similar things within the compiler. So here's a simple example. We've got the same arithmetic operator from before, and what I'm doing now is I'm decompiling that to a kind of pseudo-code. So it's the same operations we saw before, but now things are written out like a compiler, like a normal program might understand. So T1 is the parameter 0, so X. T2 is the parameter 1, so Y. And then T4 is T1 plus T2, and then we return T4. And this is all within something we call a block. So there's a label like you would with gotos in C and things like that. So it's a pseudocode. It's not really Java code, but this helps them understand what's going on. So now the graph we have is much more linear, and you can read it from top to bottom and left from right like you would do with Java code. If we look at an example with control flow, here we have statements such as if T6, and T6 is T1 equals T5, and they're the parameters and comparing things, then go to B1, else go to B2. And then you can see which code is run within those. What I'm trying to do over time is restore a structured if as well. So you see if, and you see curly brace for the true, and then else, and the curly brace for the false. So what problems can we solve this? And this is the so what, and the interesting bit from this whole talk. We said we'd like to understand what the JIT compiler is doing, gain more knowledge of how the JIT compiler works and what it does, and maybe resolve some queries in the workplace or online about what the JIT compiler is doing or why. And we can give a couple of concrete examples here that I've seen people actually debate and not know how to answer. Without looking at what the compiler is actually doing. So lock collision. You may not be aware that if you have two synchronized blocks next to each other and they synchronize on the same object, then will Java release the lock between these two blocks? Right, so it's synchronizing on one object and then it's synchronizing on the object again. Will it acquire and release the monitor twice, or will it acquire it once and then keep going? You may think, why would anyone write code like this in the first place? Well, code like this tends to end up after inlining, for example. So if you have two synchronized methods and they're called one after the other and they're both synchronized, then will Java release the lock between them, or will it keep hold of them? Well, we can answer this for ourselves using Seaton and this tool we're talking about. So, so what we have when the compiler starts, if we look at the graph decompiled to this pseudocode before optimizations are applied, we can see a monitor enter, which is the start of a synchronized block, and monitor exit, which is the end of a synchronized block, and we can see the store field inside it. And then we have acquire it again, so we monitor enter again, we store the second field, and then we monitor exit again. So at the start of compilation, there are two separate synchronized blocks, and we require the lock once, and we release it, we require it again, and release it. The first thing the compiler does is it lowers the program. This means it replaces some high-level operations with some lower-level operations. So the program gets a little bit more complicated before it gets simpler, but we can still see here we've got an enter and an exit, an enter and exit. It's just there's some more stuff about how to use the object that's been expanded out. But then as the compiler runs, we can look at the graph, the data structure inside the compiler at a slightly later point, and we can see actually it's combined the two synchronized blocks, because we can see now there's only one monitor enter or one monitor exit, and the two field writes are actually right next to each other. So we can answer this for ourselves. Yes, the Java JIT compiler, or at least Graal, I think Hotspot does as well, will keep the lock while it runs two back-to-back synchronized objects. We can answer that for ourselves by using decompilation and compiler graphs to look at what it's doing and why. Another example, say we've got a vector object, so it's got simple x and y, and let's say we've written everything quite a functional way, so it's final, and adding produces a new vector. And then if we want to sum but only get the x component, we would do a add and then get x. Now the query is, does this allocate a temporary vector object? Some people say yes it will, some people say no it won't, the JIT compiler will get rid of it. Well, let's find out by asking the JIT compiler. And again, this is covered in a blog post in much more depth. But here we go, when the JIT compiler starts running, before it starts optimizing, we can see it creates a new vector object, and we can see it stores into the vector, and then it loads out just x to return it. So it returns t10, and t10 is loading out the x from the object it just allocated. But if we let the compiler run, we let escape analysis run, which is an optimization to get rid of object allocations, we can see, right, all it does is it takes the vector, the two vectors in, you can see it loads x from the first one, it loads x from the second one, it adds them and returns them. So although we wrote a method which looks like it allocates an object, so it looks a bit wasteful, we can see actually the JIT compiler can show us that it is removing that allocation, and actually it's doing what you might do if you manually optimized it. Something that Seaton can also do, if you still want to see assembly, Seaton can also show you assembly. So it includes a tool called CFG2ASM, and this tool doesn't need that annoying HSDIS file. And it will give you some assembly output as well. So we can see the assembly if we want to with our tool, but we can also use it to answer questions like, will the JIT compiler combine my synchronized blocks? And we can use it to answer questions like, will the JIT compiler remove the allocation of this object, which I think isn't needed. So that's just a little jaunt through the Graal JIT compiler and the Graal graphical intermediate representation, and Seaton and decompilation, and how I think it can be used. It can also be used for other applications, such as looking at how Ruby is compiled by Truffle Ruby, or looking at how your code is compiled by ahead of time or AOT compilers like Native Image from the Graal VM if you're using that. It's a prototype development tool, not a product. It's open source and on GitHub. If you'd like to use it or improve it, please get in touch and share what you're doing with it. Thanks very much for listening.
Thank you, Chris. This was awesome. I have a few questions. I think maybe the audience would like a little bit of background on HSDIS. because I know you spoke about it. So it's basically associated with the hotspot disassembly, and that's why it's HS for hotspot.
Yeah.
But would you like to provide how it's dependent? It's different for different architectures and how it's dependent on the assembly.
Yeah, so it's effectively a plugin architecture. So the idea is that Hotspot can dump out machine code. By default, will just give you the raw bytes, which almost nobody can use to do something useful, even someone who's experienced with working machine code. So they raise a plugin architecture where you can plug in a tool to do something else with it, and normally you just print out the actual assembly code that you'd like to see, as if you used a debugger or something like that. Now, for complicated licensing reasons that I don't fully understand, and I'm not a lawyer, so I wouldn't choose to try and explain, it can't be bundled by default. I think it's built on a library that isn't compatible with GPL and the way it's used in Hotspot. But the reason doesn't matter why. The problem is that means that people won't distribute it normally. So you have to go and find your own. So you can go and download one from a dodgy website, or there's some reputable ones as well, or you can try and build it yourself. But it's a bit of an awkward piece of software just to build. So building parts of JDK on their own aren't very fun. But they're trying to improve this actually. So as well as using a tool like Seaton, where the machine code gets written to a log, and then you can use that tool offline to decompile it. I think they're trying to plug in now standard, permissively licensed decompiler. So the situation should get better in the future. But at the moment, it is a really awkward little wart on trying to look at assembly. Yeah.
It's true. When we did the Windows on ARM port, of course, we had to generate our own, have our own HSDIS for Windows on ARM, and we used the LLVM compiler to do that. And now I think we are trying to get it out to OpenJDK so that it can be, it's kind of better licensing agreement and everything. So it could be a part of OpenJDK. So let's see where we get with that. I had another question, but I want to check if somebody, there is a question in the chat.
So there's a question about native image, yeah. So native image, if you're not aware, is a compiler from Java code to native machine code in the same way that a traditional C compiler runs. So you give it class files and it produces an executable, and that's a standalone executable. It includes everything you need to run it. And the great thing about Graal is it actually does this by running the same compiler as the Graal JIT compiler, just slightly reconfigured, so it doesn't need any extra support. And then they write the machine code out to disk. And you can use CFOAM and the decompiler to look at how it's compiled that ahead of time code in exactly the same way. So you can see what code you're really going to run. I think native image also produces some other logs in the same graph file format. So I think it might give you some information about which classes call methods on which other classes and things like that. So I think you can use it to look at that as well. And also, if you know about Truffle, I won't spend ages explaining Truffle in depth because it's not massively relevant. But if you use Truffle, which is a system for building compilers automatically, you can use it to understand what Truffle is doing and why. And lots of data structures in compilers are graphs. So it's like a common point of communication and a common point of tools for understanding compilers is being able to look at things in these graph representations.
There's another question about how this will help with finding out errors at the time of compilation.
So it's pretty rare that there's an error from the JIT compiler. So remember, we're making a distinction here between the header, the Java source code to class file compiler. That's Java C, and we're not talking about that. So we're talking about when at runtime or ahead of time it's compiled to machine code. And it's extremely rare for the compiler to miscompile something. If it does, then yes, CFOAM is a very good tool for using that. I think something's gone pretty wrong if even an advanced application developer is trying to debug the JIT compiler. But we could expand your definition of errors to be compiled in a way you didn't like. So if you were expecting the JIT compiler or depending on the JIT compiler to work in a certain way. So we have people who, for example, build low latency applications, and they don't want any allocations. For example, what they could do with CFOAM is they could look at all the graphs involved in their application, and they could programmatically detect if there were things they didn't like. So you could actually use it to test that your program isn't allocating anything. And you can do that for more subtle things as well. Something we did at Shopify once is we were trying to add a new optimization for boxing. So, you know, boxing is where you have a capital I integer. And we had some things being boxed and unboxed that we didn't think should be. And we wanted to argue to the Oracle team that they should implement a better optimization to get rid of them. And Oracle said, well, we don't think it's that relevant. This probably doesn't appear in reality. So what we did was we dumped out all the graphs for running our production application. And because Seafoam is a library as well as a command line application, we wrote a little program to use the library to query how often this pattern of boxing and unboxing appeared. And we could say, well, it appears in this % of graphs and this % of time is being done unnecessarily and things like that. So you can use it to reason about your code and how it's being compiled. And we're thinking about using it in tests. So to sort of, you know, test that something is compiled in the way we like, rather than manually checking it or monitoring the performance. If you want to test it in CI, you can check the graph and say, it has compiled like I wanted. That's good. And assert it.
I think the last question that was there about how do you find it helpful to find during the optimize the running time of the code. I think you answered that with your example. There is one asking about no additional optimizations and recompilations to machine code at application runtime. So I'm not sure.
Yeah, so not all code is just-in-time compiled, but if it doesn't get just-in-time compiled, then by definition you're not interested in what the JIT compiler would do with it because it hasn't been called enough to make it useful to do so. But something you can do is you can understand why code's been recompiled. So often you'll see, say you have code which goes to one of two branches, and it says if X, then do this, if Y, then do this. And if your program starts off by just calling X, then it'll only compile X into the generated code, and it will leave Y as like a cutoff part that says we've never seen that happen, so we won't compile that. And then you can see the second time it's compiled, if you start using Y, it'll compile Y in. You can see which parts of your code have been compiled in and not. So you can see if things like your error conditions or your say you write a method that has something that's designed to handle most cases, and then something that's designed to handle degenerate cases that you only encounter rarely. If you look at your graph and you see the degenerate cases being used, then you think, oh, well, my optimization isn't quite working. I'd like to not compile that. In native image, if there are no additional optimizations or recompilation of machine code. Yes, in native image, can't optimize quite as aggressively in all cases as the JIT compiler. That's because of the JIT compiler can optimize your code as it's actually being used. So it can observe the runtime values flowing through the program. It's called profiling. And native image has to be a little bit more conservative because it doesn't know what value is going to run through your program. So a good example in the system I work with is if you have a function which adds together two numbers, and one of the numbers is always the same. So say you have a function called add, and it's only ever called with 1 and then another number, it'll turn that into an increment operator automatically because it sees what the values actually are. How do you install it on Windows? I'm not a Windows user, sorry, Monica. But it's a Ruby application, so it should work on Windows. If you'd like to try running on Windows and it doesn't do what you'd like, then please do open an issue and I will fix it as quickly as I can. I'm trying to do a website version of it as well, so you can just run it online, so that you don't need to. We're looking at doing a like an Atom version as well. Not Atom, I mean Electron version. So it's just a graphical application, so it's a bit easier to use. How would you affect the running machine code? Well, that's where it gets tricky, right? So the graph can tell you what may not be ideal or may be wrong in your mind, but how you fix that is then up to you. So we do a lot of optimization, deep optimization of Java stuff in my job because if we're implementing another language, Ruby, on top of Java. So we're trying to make that fast so it's fast for everyone else. And what we do is we look for things in the graph we think shouldn't be there, that we don't want to be there. So what's a good example? So if we see a method call, we think that should have been inlined. I don't know why we're left with that call. Then we'll go and examine why that call is still there. And these graphs include quite a lot of debugging information, so you can query why that node, where it came from, and why it's still there.
So that leads to one of my questions. So what are the other options with respect to the dump, the graal.dump? You said one was the one that you used, but can this support, CFOAM support other options, and how deeper?
Yeah, so what you can get it to do ultimately is you can get it to dump out the graph before and after every optimization. But there's, I don't know how many optimizations are on Graal. I'm guessing off the top of my head, like 50 or something like that, 50 major phases. So that turns out to be a lot of files very quickly. So the number can set the verbosity of it. So you may want to see major phases, not all of them, because otherwise you get a huge amount of files on your disk. So you can configure how many numbers are seen, how much verbosity is. You can also get it to only print graphs for certain methods, and you can just constrain what you see, so you get a lower volume of stuff. It also makes your application run slower because it's doing a lot of I/O to write out these graphs, things like that.
So I'm going to give the last minute last question. Why do you use Ruby on top of the JVM? Is it for performance? Is it for the tools? Is there anything?
It's mostly for performance, but also about tooling. So GraalVM lets you run other languages on top of the JVM, and the JVM has absolutely world-beating functionality in terms of compilers and garbage collectors and stuff like that. We'd like to reuse that for Ruby at Shopify. So that's what we work on. We're re-implementing Ruby on top of the JVM. It's similar to another project you might have heard of called JRuby, which is also Ruby on the JVM, but trying in a different way. It's a polyglot thing.
So there's one more question, but before that question, I encourage everybody to join us at the Zoom room. It'll be right after, it's the link right after the link for this particular session. So click on the link, please join us there. Please turn on your cameras there and share your questions and thoughts over there as well. I'll pop in there briefly right after the session, and I hope to see you there, Chris, as well. The last question goes, in your experience, how often does CFOAM lead to refactoring of high-level Java Ruby code versus recommending new JIT optimizations?
It's almost always refactoring the Java code to make it more amenable. So Java's optimizations work really, really well, and they're almost always good enough to do what we want. It's just sometimes you have to phrase your things in Java in a slightly different way to persuade it to work. And maybe we can make the optimizations better, but there's complicated rules in the Java language that the JIT compiler has to meet. So the JIT compiler has to always be absolutely correct for your Java code as per the spec. So sometimes it's just a case of slightly restructuring your code, a little bit refactoring. It's important then to comment, because it means we end up with Java code that on the face of it, you think, well, it'd be written like that. And there's a reason that pleases the JIT compiler. And now I say that, it doesn't sound great, actually. Maybe we should make the JIT compiler optimizations better.
Well, thank you for your time, Chris. I'm so glad that you could join us at QCon. And this was awesome. And I learned a lot from here. I'll see you in the Zoom room. Thank you all.
Thanks.